Good afternoon. It's my pleasure to be at Google to deliver this seminar. The title is Issues and Experience in Designing Real-Time Collaborative Editing Systems. My name is Chengzheng Sun from the School of Computer Engineering, Nanyang Technological University, Singapore. This talk will consist of two parts. The first part is focusing on the collaborative editing algorithms and technique design. The second part will be on the system design. And both parts are based on over 15 years exploration of collaborative editing technologies, from 1D text editing to 2D word processing and 3D digital media design collaborative editors. First, algorithm design. And this part, we need to have a clear definition of what is called collaborative editing. A general definition is that a real-time collaborative editor allows multiple users to edit the same document at the same time over the internet. As you can see, these are the familiar logos for the famous real-time collaborative editors. And Google Docs is there. That explains why I'm here to give this talk. And also two systems, and I'm going to explain in more detail. That is from my group, CoMaya and the CoWorld. For this general definition, we can have many different interpretations about what is real-time collaborative editor. I want to elaborate the following points. A real-time collaborative editor is an editor which is no different from the ordinary editors you are using with conventional functionality, still an editor. Secondly, a real-time collaborative editor is different from the editor you are using because it is able to support multiple users to edit the same documents at the same time. And finally, the notion of editing is generic in this context. An editor can be used to edit a wide range of different documents, including text, graphics, spreadsheets, image documents, and also includes CAD, digital media design, digital media models, computer game states, and virtual environment states. Another important point in the CE system is that human users are part of it. And in this context, we see a hierarchical structure of communication protocols. In this structure, on top of that, we have two users, and they are also communicating with human protocols. And collaborative editing designers are not interested in anything below the application layer in the hierarchy. Starting from application layer, we design application protocols. And if we are restricted to this area, this is a conventional distributed computing or internet computing research focus, and we cover this part in our research. But our system is not just a distributed system, it is also involves human-computer interaction, human user part of the system. And this is also not a single system, it involves multiple users collaborating over the internet. So altogether, this is the scope of our study. It involves distributed computing, human-computer interaction, and collaborative computing, and involve human users. And with user in the system, we have some special challenging issues. And also human users can make some of the solutions easier, some of the problem even harder. The first issue, which is related to human users, is the interactivity experience. Human users have been using editors for so many years. They had good interactive experience with single-user editors. They would expect to have similar experience. So we should aim at achieving the same interactivity experience. However, in the internet environment, communication latency is much larger than this interactivity requirements, much higher than 100 milliseconds latency threshold value. And also we should realize latency can be improved by technological improvement, advancement, but there is an ultimate limit. That is limited by the speed of light determined by the law of physics. Eventually, the total round-trip delay around the Earth is 200 milliseconds. We can't go beyond that. And 200 milliseconds is doubling the 100 milliseconds threshold value. So we need a way out. We can't get rid of latency, but we can hide it. A technique to achieve quality interactivity in the internet environment is latency hiding. That is to create the illusion that latency is lower than it actually is. So that's what we call the magic of latency hiding. A widely used latency hiding technique is replication. In the collaborative editing context, the editor and the shared document are replicated at all collaborating sites in the collaboration session. The operations are first executed locally to achieve high responsiveness, and then propagated to remote sites for notification, also for maintaining consistency of replicated copies. The main challenge in the replicated collaborative editing environment is how to maintain replicated documents consistency in the face of concurrent editing operations. There has been a lot of research in the past decade, and one consistent model specially designed for collaborative editing system was published 10 years ago in 1998 with 3 consistency requirements: convergence, causality-preservation, and intention preservation. In the following slides, I will go through the 3 requirements one by one. Convergence requirement is the requirement that all replicas of the shared document must be identical after executing the same group of operations. Taking text editing as an example, these 2 users, starting from the same text string, 1 to 2 characters. Initially, the document is identical, and 2 users can independently generate 2 editing operations. One is to insert X before 1, 2, another is to insert Y at the end of the text. These 2 independent operations can be executed immediately to achieve high concurrency and also achieve high responsiveness, and also generate temporary divergence. This divergence is tolerable and acceptable to these users. But after these 2 operations propagated to the remote sites, we require after executing the 2 remote operations, the final document should be the same. That is the required by the convergence. Secondly, we need to preserve intention. What is intention? Intention is the local effect of operation. When you generate the operation, it has a local effect. But when the operation is executed at the remote site, that effect should be preserved in the face of concurrency. Because maintaining identical documents is not good enough for the correctness of this system. We need also to preserve the intention. Taking text editing as an example, initially document states A, B, C, D, E, and then at the same time 2 concurrent operations generated. Insert 1, 2 at location 2. The intention of this operation is insert 1, 2 at position 2. That's clear. And another operation deletes at position 3 2 characters. That is to delete C and D. That is the intention. That's the local effect when the operation is generated. We want to make sure that effect is preserved at all remote sites in the face of concurrency. Now, after propagating these 2 operations to remote sites, on the right-hand side, the operation is executed in the original form, and this execution is able to achieve the original intention. And that intention is to insert 1 and 2 between A and B. That is done locally and remotely. And the deletion also happened to accord to the correct 2 characters. C, D are deleted. But on the other hand, when this delete operation is propagated to this site, if the operation is executed in the original form. The deletion will incorrectly delete two characters, which is not CD, but one is 2, another is B. These two characters are not intended by the original operation. So this is called intention violation. The correct result should be this one. Should be this one. Now you may ask, what's the difference between intention preservation and convergence? Convergence only requires the two copies are identical. They could be identical on the wrong result. The intention preservation add another criteria, so you should be correct on this copy, not this one. So if we are able to force both sides to achieve this result, we achieve convergence, but we lose the original intention. That is intention violation. So both criteria together ensures a correct and consistent result. The third criteria is about causality preservation. Operations must be performed in their natural causal effect order. This time we need to take 3 sites as the example. Still text editing, suppose one user just type a question, artificial question, very simple. 2, what is the sum of 2 plus 3? And propagate this operation to other remote site. And suppose this operation arriving at the middle site first. And this site see this result and then respond with the answer. The sum is 5. So sum is 5 following the previous question. This is the right result, but we notice this operation arriving at the middle site first and then arriving at the third site. But this operation, causally after this operation, because this generated the answer to the previous question, happened to arrive at the third site earlier than the question itself. Their natural causal effect order has been reversed. And in this case, the user at this site will be confused by seeing the answer before the question. And in other cases, it could be the one operation is to create an object. The other operation is to delete the created object. The deletion may arrive earlier than the creation. In that case, the system can be confused by seeing the deletion before seeing the creation. And in all cases, causality violation can cause the confusion to both the system and the user. And this has to be corrected by delaying this execution. And in this order, in that way, we can maintain causality. And I should point out, maintaining causality is a classical technique issue in distributed computing. There are many different techniques to ensure this. And I'm not going to explain what technology can be used. There are plenty of them to choose from. What I will focus on the technique which is able to achieve both convergence and intention preservation. That is the special technique invented by collaborative editing researchers. The technique has the name operational transformation. As I said, this technique is able to achieve both convergence and intention preservation, but at the same time, it doesn't impose any restriction on the users. That is the very important feature of this technology. Unlike other traditional distributed computing technology like locking and serialization, they impose restrictions on the user side. And as we point out, users are part of the system. The technique should meet users' needs and shouldn't restrict users' interactivity. And there is a paper on this Soviet paper on operational transformation that was also published 10 years ago. And you can find a variety of operational transformation techniques there in detail. Now, in this context, I will give you one slide to explain the basic idea of operational transformation. Still taking text editing as an example, starting from identical document 1, 2, and 2 independently generated operations. And look at this. This operation is to insert character Y at position 3. Now, with operational transformation, a remote operation arriving at the remote site, it will not be executed in its original form. It will be transformed against another concurrent operation. concurrent operation. In this case, this transformation doesn't change anything with regard to this parameter. There's no change. For what reason I will explain later. But on the other hand, this operation, when it arrives at this site, operation 2 will be transformed against operation 1. The parameter position, reference parameter 3, will be transformed into 4. The reason is to take into account the effect of this concurrent operation, because it inserts 1, x, on the left side of this string. And that push the correct position by 1 to the right. So to compensate this push, we change this parameter to make this operation right. That is the basic idea of operation transformation. And to make sure operation transformation works correctly, there are a large number of properties for the transformation system to maintain. One of them, which is directly related to this scenario, is the following. The two concurrent operations can be transformed in any order and also can be executed in different order, like illustrated in this scenario. And we must make sure after transformation and after execution them in two different orders. So O1 followed by O2 prime, that's transformed. Now if you execute O2 first, then followed by O1 prime, the final result must be identical, That is one of the many consistency requirements, transformation property requirements. Another fundamental assumption for operational transformation is that data objects are linearly addressable. We use text editor as an example to illustrate this. But actually, these objects can be any other type of object. The essential requirement is not to be the text, to be the character. It is their relationship must be linearly addressable. It can be a graphics object, can be a slides, can be any other object. 3D, 2D don't really matter, but that relationship is fundamental. Now, that's the basic idea. A system, or OT system, is a complex system, consists of two major components. One is the control algorithm at the top, which determine which operation are transformed against others according to their concurrency or context relationships. These are the generic relationships, independent of operation type. The second part is operational OT transformation functions. These functions directly transform a pair of operations based on their types, their position parameters, and other operation-specific attributes. In between, we also have implicitly defined the divided responsibility between control algorithm and transformation functions. These functions, these responsibilities are formulated in the form of criteria, conditions, properties, and we can use them to formally verify whether consistency, whether transformation function or control algorithm meets these requirements and ensure the aspect of correctness, because the correctness is defined by a set of properties. Now, with this framework, I will give a very brief coverage of using examples to explain the transformation functions and then control algorithms. For functions, I give you just one slide to show a whole OT transformation function for two primitive operations, delete and insert, can be expressed in a single slide and in nearly formal specification. In this context, we deal with characterized single character editing. And I should point out, all the text editors can be based on these two primitive operations. In other words, this slide contains the full set of transformation functions for plain text editing. Now, look at this. II means transformation between two insert operations. I stands for insert. And take one insert, another insert, and we compare the position parameter left or right to determine whether the later operation should be shifted by one position under certain condition. Otherwise, no shifting. And we do similar things to -1, +1, -1 for other combinations. The idea is simple. Just compare this, whether it is left or right, to determine what action to take. The idea is very simple. But I should point out, actually, transformation function design, even though this looks very simple, there are a lot of intricacies involved, particularly related to two tie-breaking issues. One is the insert tie, when two operations targeting at the same location. How to break the tie to ensure consistency. When two delete operations targeting at the same character, how to resolve this conflict and achieve a consistent result. For insert tie breaking, it is straightforward. We use some serialization. Actually, in this example, we use user identifier. Suppose user identifier are identical to break the tie. For delete, serialization, any kind cannot achieve the correct result. The correct result is to maintain, to ensure that only the first delete takes effect. The second delete should not have any effect. And this effect is not achievable by any serialization protocols. And now this seems to solve this problem, but actually it's far more complex than what I have shown there. For delete tie breaking, for concurrent execution of these two operations, the result is correct and easy to achieve. But when we have group undo, if we want to undo one delete, what happens? What's the effect? If both users undo the same operation, the same delete, then what happens? So this causes a lot of problem for undo. And insert tie breaking also is non-trivial. There are some well-known force tie problems. They are not actual ties. The force ties can be caused by under various circumstances, and that is not an easy task. And you can find in literature. And also, if we extend the transformation from single character to a string of characters, the complexity also increases. And that is why still there have been quite some research going on, and most of the problems have been solved, and the system, and also there are usable, robust system available out there. Now, control algorithms. The first OT control algorithm was proposed by the team led by Ennis at MCC and published in 1989. That was 20 years ago. And this was the pioneer work on OT. And this work has inspired many researchers to follow this line of research. Part of the reason was the original algorithm, the puzzle, or the flow inside the original algorithm. And this flow has the name, the DOPT puzzle. The name of DOPT was the original algorithm's name. The puzzle can be illustrated in this way. In my previous slides, I showed the basic idea of OT with two concurrent operations. And I show how that can be transformed correctly. And the original algorithm works for this kind of scenario. But if we add one additional operation to the scenario, we can immediately defeat the original algorithm. Immediately defeat that. And this counterexample was independently discovered by several research groups in the 90s. And this operation is obviously different from this operation in their relationship with this one. This operation, and they are concurrent, but they are sharing the same document state, or we call them the same context. This operation is also concurrent with this operation, but this operation's definition context is different from this one because the document has been changed by this operation. So the parameter of this one and this one are not comparable, cannot be used using the simple transformation function to adjust their position. And this is the simplest scenario to show the intricacy in design OT control algorithms. But actually, in this system, we allow user to generate operation at any moment of time. And if you add one more operation there, the scenario becomes more complex. And if you add one more user there, with one additional operation, the picture is getting messier and messier. And if you have n arbitrary number of users and they generate operation editing any object at any time, then the scenario is overly complex. Fortunately, over 10 years researchers have found solutions to this problem. And one of the solutions was from my group, and we designed the generic operational transformation algorithm, the GOT algorithm, which is based on the use of a pair of reversible transformation functions. One is IT, stands for inclusion transformation. Another is ET, exclusion transformation. And this is just a diagram for this algorithm. We take the new operation as one input, and also we use a linear buffer called history buffer to log all the executed operations, feeds into the algorithm which use these two transformation functions, and then produce the output. The internal details are intricate. This is not the place to explain, but it's important to point out the use of these two transformation functions. This IT means AO is a new operation, so OA is the input, OB is the operation stored in the history. And when OA transform against OB in the inclusive way, we produce OA prime. And this OA prime is another version of OA which has taken into OB's effect into consideration in defining the parameters. That's the meaning of the inclusion transformation. So we use plus, minus. This is to exclude the effect of this operation. Exclude the effect means if this operation was not executed, then what their parameter should be. Then we produce another version of this operation. And we must ensure these two functions are reversible in the following sense. When OA transform inclusively against OB, and then exclusively against the same OB, we should be able to get the original operation back. And since this work, we had a number of follow-up work on top of GOT algorithm. The first one was 1998, the GoTo algorithm. It was an optimized version of GOT. And any undo algorithm is to extend the concurrency control to group undo to support undo any operation at any time. And this algorithm is integrated with this. And in recent year, the newest result published 2 years ago and also extended in this year, it's COT algorithm, context-based operational transformation. This is based on a new framework of theory and also with a new capability, with the integrated capability for supporting do and undo at the same time with formal proof and implementation. In over 20 years, OT has evolved to support a range of collaboration functions, including the original function, that is to maintain consistency, also called concurrency control. And later it gains the capability to support undo any operation at any time, and conflict resolution based on object-level multiple versioning, also based on OT. Workspace awareness can be supported by OT as well, and we invented the new technique which is called object-associated telepointers and radar views. Optional locking, locking is useful to help solve semantic consistency problem. And with the support of OT, we support a lower optional locking technique in the internet environment that is more fine-grained and also responsive. Flexible operation notification and compression is a set of techniques based on OT, which is able to bridge real-time and non-real-time collaboration. So we can use the same OT technique to support real-time editing and non-real-time editing by multiple users. And most of these techniques were invented in the context of group text editors, which were developed mainly for research purpose as a research vehicle, such as the REDUCE projects conducted by my research group. And in recent years, OT is increasingly being adopted by commercial collaborative editors. And one example is the sub-ether editor. This is the commercial text editor, and it's well known, and it is based using OT technique. And there are others as well. Okay, so much about the technical aspects of collaborative editing. Now we move to the second part, is how to design useful system using the advanced collaborative editing technology we have developed over the years. And there was an article published 2 years ago, which is about how to convert single-user applications, existing single-user applications, for supporting multi-user real-time collaboration. First, the design of the collaborative editor, in our view, we have an important observation about the system. A collaborative system contains two orthogonal sets of functions. The first set is conventional editing functions. The second part is collaborative functions. These two parts should and can be separately dealt with. Based on this observation, we have two design goals. The conventional functionality of collaborative editor should have as rich functionality as their single-user counterparts. This is the set of single-user, just a sample set of single-user editors out there available. If you want to develop a collaborative version of something in that domain, make sure your collaborative version has similar, comparable functions. As we point out, collaborative editor, still editor. Conventional functionality should be as the same. Now, because we have large, already mature, widely used commercial products there, can we take advantage of these existing single-user editors in building multiple-user collaborative editors? That's the question. The second design goal is to make sure collaborative editing systems to have collaborative function comparable to advanced research prototypes. As I point out, most of the advanced techniques were invented in research prototypes. These prototypes do not have rich conventional editing capability. They are not regarded as useful application, but they have advanced collaboration capabilities. This is just one example. This is the old reduced text editor with a list of advanced collaboration capabilities. But this interface is very simple with limited editing capability. And it was implemented in Java applet and in a web environment. That can be regarded as one of the early web-based real-time collaborative editor in the 90s. Now, the question is, can we avoid reinventing collaborative technology in building various collaborative editors for the end users? Can we directly use the developed technology rather than reinventing them in the commercial system? Now, motivated by these design objectives, we propose the transparent adaptation approach to build useful and advanced collaborative systems without reinventing the wheel. This approach has one component, single-user option component. Another component is a collaboration engine. Single-user application component provides conventional functionality which can be either existing or new application, can be proprietary or open source, can be desktop or web-based, doesn't matter. But the engine part should be able to support a range of collaboration functionalities, such as concurrent work, as well as relaxed what you say is what I say, and good responsiveness and group undo, etc. We further refine the collaboration engine part by decompose the application-specific collaboration functionality from the generic collaboration functionality. The generic collaboration functionality is OT-based and can be used for a wide range of different applications. And the adapter is providing this application-specific collaboration capability and bridging the generic engine with the application using their API. And with this approach, the design of a collaborative editing system is reduced to the design of the adapter, which is significantly simpler than reinventing functionality there and reinventing functionality there. But still, I should point out, the design of collaborative adapter is not only an engineering challenge. It also involves research, particularly when you apply this approach from one domain to a new domain. You always need to do initial research. For Office, if we have done Office for one example, it's easy to apply similar adaptation technique to another Office application. But if we extend that to 3D design, then new research is needed. So this is the approach we propose. We want to reuse the engine, reuse single-user functionality, and focus on inventing bridging techniques. We apply this technique to Microsoft Office tools. The initial research choose Microsoft Word and PowerPoint as our initial target. As you can see, these two systems share the same architecture. They use the existing application, they use the same engine, but we built two different adapters. And these two adapters are quite similar because they are all Office elements and also from the same vendor, quite similar. Now, the following slides, I will show some of the technical challenges in the adapter, what we call transparent adaptation happening inside this adapter. So we use Word as an example. What kind of technical challenges there? First, from the single domain, one domain, plain text editing, to two domain, word processor. As you can see from the interface, this is directly matching the OT linear addressing space. But this one doesn't look like that. These two-dimensional objects can be positioned in the visual space at any place and has no relationship whatsoever. So this appears to be the main obstacle initially to applying our generic engine to this application. But the main discovery made by collaborative Word, CoWord project is that we find the application Word API, the general public API, actually provides a wide range of ways of addressing these objects. Even though these objects visually unrelated to this linear addressing system, but the API has something related, not obvious. We use our overview, our technique, to extract a subset of existing Word API and map all these objects into a linear system, and that is existing in their API. We are not inventing anything. We are not changing anything. Also, we don't have access to their source code. And in this way, after this adaptation, the engine can be plugged in. And we did a similar thing for the PowerPoint. PowerPoint this time has a hierarchical linear addressing system. Actually, Word also is hierarchical. The previous slide is a simplified version. PowerPoint document has a sequence of slides. At this level, we have a linear sequence. And for individual slides, it has two independent addressing domains. One is text. It is directly corresponding to linear addressing space. This graphics part also actually has API to address them linearly, existing in their API. You don't need to invent it. And just find the way. We call this as discovery rather than an invention. It's a discovery. It can be used in this way. Then after you establish this mapping, of course, the original OT data model is a single linear model. We need to extend the OT core technique to a hierarchical linear adjacent space. This is the general tree of linear adjacent domain. We don't need to go to the detail. Suffice to say that all the data models, those data objects in word processors, PowerPoint documents can be mapped into adjacent space compatible with this. They are just some instance of this general form, the so-called X extended OT data model. This is one part of the adaptation we call a data adaptation. Another part is the operational adaptation, because the commercial application has comprehensive, also sophisticated, high-level user accessible functions, which is far more complex than insert, delete, two operations. And in the original OT model, there's no update operation. So our first extension is to add one generic primitive operation, update, into the core OT technique. And in this way, many user-level operations can be mapped to update, including text update operations, and also graphics operations, like this file filling, moving, and also rotation. They are all update operations and can be captured by this single primitive. With this core extension, this is still not enough. Users generate operations much higher level. Then we need application-specific extension to OT. That extension, on one side, we take the core OT 3 primitive operations. Another side, take the API, a comprehensive, complex API providing various operations methods for the application programmer to access. For user interaction, we generate operations we call adapted operations, AO. This group of operations should be the art of operation adaptation largely inside this part. We should encode the user interaction at a higher level, which captures sufficient information for OT processing and also for API replay. And also we do two-level adaptation. One is to adapt the AO user-generated operation to the OT required primitive operation to handle any issue caused by concurrency, consistent maintenance, group undo, etc. This adaptation is done there. And also we use another level adaptation to get the semantics right. This level is get the syntax right. And this is the art of operation adaptation. So after solving these problems, we get the code up and running, but I should point out the system, initially we advocate the collaborative editor should support multiple users to edit any object in the document at any time, and so users are unconstrained, free access. That model is what we call multiple actor, multiple view. So anyone can edit the document at any time. It's a highly chaotic, uncoordinated process. And the technique we invented in the collaboration engine is able to support it. Once we are able to do this hard work, it's easy to extend to support other different combinations. For example, we can have multiple actors. They are editing a synchronized view, the same view. Anyone can edit it, but they have a synchronized view. If the view change, everyone will change to a different area. Also, we can have a single actor, a single view, if you want to sequentially impose sequential interaction among group members. That can be easily done. And also, we can have single actor, but allow multiple users to view different parts of the document. And these are just the 4 combinations. We have more combinations on top of that. What we learned from this, once you have an infrastructure which is able to support this, it's easy to support other more restrictive form of interaction. But if the technique was invented only for a restricted form of interaction, it would be very difficult, if not impossible, to support more liberal interaction. That's the lesson we learned. Now, there is a public available demonstration at this location in Singapore, NTU. This picture gives you more detailed internal component description of the adapter and the engine. We are not going to explain this detail. Rather than that, I would like David to help to give a live demo for this system. That will be more interesting. And we switch to the real system. Okay.
All right. So this is the CoWord system, and as you can see on the left-hand side, this is the main editing window, and it's identical to Microsoft Word. And on the right, we have this collaboration widget called the Radar View. Okay, the Radar View provides information about where users are looking at in this document. So if I scroll through this document, you can see that this Radar View is being updated, and it's being synchronized to the remote side. So he knows where I'm looking at in this document. And when our viewports overlap, we can see each other's mouse pointers. So that's his mouse pointer, and this is called a telepointer. It gives you more fine-grained user-level interaction in this shared workspace. Okay, so we can actually co-point to a particular area in this document and say we want to discuss this area. Okay, so that's the main user interface. We want to first demonstrate collaborative editing. So and to do that, we're going to just jointly come up with a list of features in CoWord, okay? And to do that, to help you see what we're typing, I'm going to turn on this highlighting feature, which color codes our text. So this is a list of collaborative features in CoWord. So so we're going to just start editing this, and I'm the green guy, and he's the red guy. Okay. So it has flexible interaction control, undoing. Okay, as I'm typing undoing, I realize that he's got undo up here, so I can use the undo button to remove what I just typed. Okay. And I actually want to turn this into a list, so let's just do that. Let's turn it into a list. I want to elaborate on workspace awareness support by saying that we have radar views and pointers. And realizes that he's made a typo here, so it's not current, it's concurrent. And it's tracking, not track. And let's update, let's update the font to bold and make it size 14. Okay. So as you can see, we can collaboratively edit not only in the same paragraph, we can also collaboratively edit in the same line in very close proximity. Okay. So that's so we want to demonstrate what we mean by well, there is a. Yep.
Is this using a local server or are you using a server in Singapore?
This is currently directly linked to that server there. Yep. But if you want to try out the latency effects, you can link to the Singapore server. So there's a feature in CoWord called multiple versioning by a single display, and we're going to demonstrate that using graphical objects. So I'm going to create, he's just going to type that up. I'm going to create an ellipse here. And the first thing we're going to try is I'm going to move this ellipse to a different location. And concurrently, he's going to change its color. Okay, so let's do that. 1, 2, 3.
Just move it.
Okay.
Okay.
1, 2, 3. Okay, so because these two concurrent operations are targeting different attributes of this object, the system should be able to merge those two concurrent changes together in the same object. Okay, so it's moved and the color is being updated. Well, you might ask, what happens if we update the same attribute? Okay, what if we change the same color attribute to different values? Okay, let's try that and see how we are handling this in our system. I'm going to update it to red, and he's going to try to update it to yellow. Okay, so 1, 2, 3.
Nope.
Okay, so as you can see, it's actually pretty hard to generate concurrent operations in the local area network. So we're going to try that again. I'm going to do red, and you can do blue. Okay, 1, 2, 3.
Oh.
Oops. Okay, it's a little hard. Okay, red again. Yellow.
And,
1,
Yes.
1, 2, 3.
No.
All right. Okay.
Try it again.
Okay. Let's
Try-
let's just do that. 1, 2. Whoops.
No. Try another
1,
one.
2, 3. Okay.
Oh,
Oh, well,
probably we did try. This is interesting feature
Uh-huh.
to say if conflict occurs concurrently, because generate concurrent conflict is difficult. But once it happens, what action we take and what kind of interface we provide, it is something of interest to many people.
All right. Let's just one more time. 1, 2, 3.
Okay. No, probably
All right.
this something is wrong.
Okay, that's we can try this offline. People want to
Yeah.
see this. Basically, what happens is that we bring up an interface that records all the possible versions that people create. So if I change it to red and it changes to blue, we record all these versions, and we provide a scrolling interface, a browsing interface that allows the user to choose which version they like, and they can commit to that version. Okay. Okay, so this is we've also.
How about we try moving this object to two different directions?
Sure. Okay.
So
I'll
you
move
move
it
to the left.
I'll move
I
it to the left.
right.
Okay. 1, 2, 3. Let go.
So
Okay.
you see.
So there we go. So
This
that's a
is it.
conflict, and the system detects there's a conflict. And if you click on the object, it brings up the interface. It can scroll through the versions. So that's the original location for the object. That's the location that he moved the ellipse to, and this is the location that I moved the ellipse to. And we also generate this intermediate version by additively combining these two moves. So it's sort of taking the coordinates and doing an average in the middle. Okay. So and a user can, of course, commit to a location. So I want to commit to my location, and there we go. Okay.
Nope.
All right.
I generate another trouble.
Okay.
operation.
So
Sorry.
let's see. One more thing we want to show is what we mean by single view, single actor, multiple view. Actually, it's multiple actor, single view.
Just a moment.
So, oh, did you log out?
Yes,
Okay.
I re-log in. You can see logging in is.
Okay, so we're logged in. So this thing synchronizes both of our views to the same area of the document. So this is to facilitate collaboration processes that require sort of revision or structured discussion. So as I scroll through this document, you can see that both of our views are synchronized at the same time. Okay. And there's a variety of different models that you can implement on top of this. Okay, so that's, and there are lots of other features, and you can try them out.
The
afterwards.
system is online, so it's freely distributed. You can try various features and report the bugs you find. And this has been shown for over 5 years. So we receive a lot of bug reports and also interesting feedback from the users. We appreciate their feedback, and also we have the system here. After this seminar, you can always interact with the system if you wish. Now let's continue with our story of this work. So after doing Microsoft Office, several representative members, we extend this technology to OpenOffice system. Just want to show this is not only related to one vendor's product. Actually, we can apply this to open source. Be aware, we're using open source Office, but we never change their internal source code. So we use the same approach, only attach their API, using their API, without changing a single line of code. Even we don't need to read the internal code to do our work. And this work was reported 2 years ago in the CSCW conference associated workshop. And next step, and the step is still ongoing, is to apply this to web-based Office productivity applications. And we find currently we have word processor prototype, proof of concept prototype, which shows the same technique can also be used there without actually, for office applications, they are quite similar. Whether it is open source or proprietary or web-based or desktop doesn't really matter.
Can you guys turn off the mic in Boulder?
Now, the more bolder step of extending this technique is to apply to 3D design tools. And the one we choose for our research is Autodesk Maya. And Maya is a 3D design tool, and we worked on this more than 2 years and produced a working prototype with similar quality as the cohort, and that was demonstrated in this month in CSCW conference in San Diego. And we also had a paper there. And we haven't write much about this system, but today I can also give a short demo of this system here, just to show the same engine driving a totally different application, 3D design tool.
So we're probably short on time. We're just going to do this.
So all right. So because of time, can we do this on offline, or they can wait for about 10 minutes?
5 minutes.
5 minutes. Do we need to make room for them?
Yeah.
Okay.
Okay.
Couple of minutes.
Right.
Let me just finish this and do the demonstration offline. Yeah. So we don't have time to do the CoMaya demonstration, but I finished the slides. I have last slide is to summarize this talk. Last decades have seen significant research development activities and achievements in real-time collaborative editing technology and systems. Existing or new desktop or web-based single-user editing systems can be adapted to provide rich conventional functionalities in collaborative tools, as proven by the transparent adaptation technology. Collaborative technologies can be encapsulated in a reusable software package, like OT-based GCE, to support a wide range of editing applications, from 1D to 3D. That's what we learned in over 15 years. What's the future of CE? We believe collaborative editing systems will become commonplace and provide seamless support for single and multiple users, for real-time and non-real-time collaboration on desktop and web-based platform over wired and wireless, local and wired area networks. So in other words, any user, anytime, any platform, anywhere, collaboration will be the future. And the harder we work, and the collaborative editor will lose its identity, because there will be future, there will have no differentiation about single user or multiple user. It's just the editor. It's naturally for all. So single user use, multiple user use the same thing. Whether you do real-time collaboration or non-real-time collaboration, the same. The same technology, the same tool. On which platform, there's no difference. Seamless support. But as we say, the best way to predict the future is to invent it. So we have time for questions in another room. And thanks for attending this seminar. And I will be very happy to take questions and have detailed discussion offline with people interested in this technology. Okay, we need to move to another room. Thanks.